For any commissioning engineer energizes hardware, a thorough study of the AC800M Compact Control Builder (CBM) project is essential. This foundational step ensures that all subsequent actions are based on a clear understanding of the system's architecture, logic, and workflow. In this video, we'll walk through the critical aspects of Chapter 1, which serves as a comprehensive guide for preparing your CBM project. From navigating the project files to understanding controller architecture and verifying libraries, each step is designed to minimize errors and streamline the commissioning process. Let's begin by exploring the project navigation and controller architecture. First step is opening your CBM project file. CBM uses CBM files or CBA archives, and it's crucial to ensure your software version matches the design office's version. This prevents library conflicts and connection issues that could delay your work. Always double-check the version information before proceeding. Once you've confirmed compatibility, you can safely open the project and begin your study. This attention to detail at the outset sets the stage for a smooth commissioning process and helps avoid unnecessary troubleshooting later. Navigating the Project Explorer tree is your roadmap through the CBM environment. This hierarchical structure organizes all elements of your project, making it easy to locate controllers, communication interfaces, I/O modules, and application libraries. Understanding this layout is key to efficient project study. Each section of the tree corresponds to a physical or logical component in the plant, allowing you to trace signals and logic from the field device all the way to the SCADA interface. Mastery of the Project Explorer tree will save you time and reduce errors. Controllers are the brains of your automation system. The PM8XX series CPUs range from the compact PM856, suitable for small skids with around 1,000 I/O points, to the powerful PM891, designed for large plants and SIL2 safety applications with up to 12,000 I/O points. Selecting the right controller for your project is crucial, as it determines the system's capacity and reliability. Always verify the controller model in your project matches the hardware installed in the field to ensure seamless integration and operation. Communication interfaces, or CI8XX modules, connect your controllers to remote I/O devices. Examples include CI851 and CI853 for Profibus DP, CI854A for PRFINET, and CI867 for Modbus TCP. Each interface supports different protocols and network topologies, so it's important to confirm the correct modules are configured in your project. Proper setup ensures reliable data exchange between the controller and field devices, which is essential for accurate monitoring and control throughout the plant. S800 series I/O modules serve as the physical interface between your control system and the field. These modules handle digital inputs, DI810-840, digital outputs DU810-840, analog inputs AI810-83845, and analog outputs AO810-845. Each module type is designed for specific signal types, ensuring accurate data collection and control. When studying your project, verify that all I/O modules are correctly mapped to their respective field devices and that the configuration matches the wiring diagrams provided by the design office. Applications and libraries are where the actual control logic resides. This section of the project contains pre-built templates, standard function blocks, and custom logic tailored to your plant's needs. Familiarizing yourself with the available libraries such as BasicLib, ControlLib, and DriveLib is essential. These libraries provide tested and reliable building blocks for common control tasks, reducing development time and minimizing errors. Always ensure the library versions in your project match the design specifications to avoid compatibility issues. CBM organizes the project into units, each mapping directly to a physical area of the plant. For example, Unit 10 might represent raw material handling, while Unit 60 covers water treatment. This structure helps you quickly locate relevant programs and logic for each plant section. Inside each unit, you'll find programs that contain the executable logic, making it easier to manage and troubleshoot specific areas of the plant. Understanding this mapping is crucial for efficient commissioning and ongoing maintenance. CBM supports two main programming languages: Function Block Diagram (FBD) and Structured Text (SD). FBD is a graphical language where green lines represent digital signals, red lines indicate analog signals, and blue lines are used for integers. Structured text, on the other hand, is a text-based language similar to Pascal, ideal for complex sequences and calculation. Knowing when to use each language helps you write efficient and maintainable control logic tailored to your plant's requirements. Programs in CBM are assigned to tasks, which determine how often the logic is executed. Fast tasks running every 10-50 milliseconds handle safety interlocks and emergency stops. Normal tasks with scan times of 100-200 milliseconds are used for motor, valve, and PID control. Slow tasks running every 500-1000 milliseconds manage trend logging and totalizer. Assigning programs to the correct task ensures that critical operations are executed with the appropriate frequency, balancing performance and reliability. CBM relies on standard libraries like BasicLib, ControlLib, and DriveLib to provide core functionality. These libraries contain pre-built function blocks and control modules that simplify the development process. Always verify that the library versions in your project match the design specifications. Using the correct versions ensures compatibility and reliability, reducing the risk of unexpected behavior during commissioning and operation. MotorCtrl module encapsulates all logic required for motor control, including start-stop commands, auto manual modes, interlocks, permissives, trips, feedback monitoring, and run-hour totalizers. Using this module ensures consistent and reliable motor operation across your plant. When studying your project, review each motor control instance to confirm it is configured correctly and link to the appropriate field devices and logic. Valve control modules manage all aspects of valve operation, including open-close commands, limit switch feedback, travel time monitoring, and modulating control. These modules are essential for ensuring valves operate safely and efficiently. During your project study, verify that each valve control instance is properly configured and that all feedback signals are correctly mapped to the corresponding I/O channels. PID controllers, such as PIDCont and PIDAV, handle process variables, setpoints, control outputs, and modes like auto, manual, and cascade. They also provide advanced features like anti-windup protection. Proper configuration of PID controllers is vital for stable and efficient process control. Review each PID instance in your project to ensure it meets the process requirements and is correctly integrated with the rest of the control logic. Chapter 1 provides a comprehensive reference for reading function block diagram, FBD logic, much like interpreting a wiring diagram. Understanding how logic gates, timers, flip-flops, counters, and selectors are used in FBD is essential for troubleshooting and modifying control logic. This reference guide is an invaluable resource for both new and experienced commissioning engineers. Logic gates are the building blocks of control logic. AND gates require all inputs to be true, making them ideal for interlocks. OR gates trigger when any input is true, commonly used for trips. NOT gates invert signals and are useful for creating fail-safe logic. Mastering these basic gates allows you to construct robust and reliable control sequences tailored to your plant's safety and operational requirement. Timers are essential for managing delays and timeouts in control logic. The ton-on-delay timer is used for feedback timeouts, ensuring that signals remain true for a set period before taking action. The TOF off-delay timer is used for seal-in timers, maintaining outputs for a specified duration after the input turns off. Proper use of timers enhances system reliability and prevents nuisance trips or missed events. The flops are memory elements used to latch or reset signals. The SR set reset flip-flop prioritizes setting a condition, making it ideal for latching trips. The RS reset set flip-flop gives priority to resetting, which is useful when a reset command must override a set condition. Understanding how to use these flip-flops is crucial for implementing reliable trip and reset logic in your control system. Counters and selectors add flexibility to your control logic. Up and down counters, CTU/CTD, are used for tracking events or operations such as counting motor starts. Selectors like SEL and MUX are used for switching between auto and manual modes or selecting setpoints. These elements make your control logic adaptable to a wide range of operational scenarios. Structured tag nomming is critical for clarity and troubleshooting. Prefixes indicate equipment type, such as P for pumps, FN for fans, CV for conveyors, M for motors, and FCV for flow control valves. Suffixes specify signal types like CMD start for command start, for running feedback, LOK for interlock OK, PV for process variable, and alarm limits like HH or LL. Mastering these conventions allows you to quickly identify and trace signals throughout the project. Find tool locates text strings within your project, but the cross-reference tool is far more powerful. It shows exactly where a variable is used and whether it is being read or written. This feature is invaluable for understanding complex logic and ensuring that changes do not have unintended consequences. Always use cross-reference when analyzing critical signals like motor start commands. Signal tracing is the most important skill for a commissioning engineer. It involves following a signal from its origin in the field, through the I/O module, into the CBM logic, and finally to the SCADA interface. This process helps you verify correct wiring, logic, and SCADA mapping. Mastering signal tracing ensures that every command and feedback is accurately represented in the control system, reducing the risk of errors during commissioning. Forward tracing starts at the field device terminal, moves through the I/O module channel, identifies the variable name in CBM, cross-references it through the logic blocks, and finally locates the SCADA interface tag. This method ensures that every field signal is correctly represented in the control system and visible to operators. It's a systematic approach that minimizes the risk of missing or miswired signal. Reverse tracing begins with the SCADA tag, finds the corresponding variable in CBM, cross-references where it is written, locates the hardware I/O channel, and matches it to the wiring diagram to identify the physical device. This approach is essential for troubleshooting and verifying that operator commands are correctly executed in the field. It provides a clear path from the control room to the plant floor. Understanding the different types of control logic elements is essential for safe and reliable operation. These include interlocks, permissives, trips, and sequences. Each element serves a specific purpose in ensuring equipment operates within safe parameters and responds appropriately to faults or abnormal conditions. Familiarity with these elements allows you to design and troubleshoot control systems with confidence. Interlocks are safety conditions that must remain true for equipment to operate. If an interlock drops while the equipment is running, such as a loss of lube oil pressure, the equipment will stop immediately. Interlocks are continuously monitored and are critical for preventing unsafe operations. Always verify that all interlocks are correctly implemented and tested before commissioning. Permissives are pre-start conditions that must be true before equipment can start, such as ensuring a tank level is above the minimum. Once the equipment starts, permissives are typically bypassed. They help ensure that all necessary conditions are met before initiating operation, reducing the risk of equipment damage or process upsets. Trips are fault conditions that force equipment to stop and latch the fault. The equipment cannot be restarted until the operator manually resets the trip. This mechanism ensures that faults are addressed before resuming operation, protecting both the equipment and the process. Always check that trip logic is correctly implemented and tested for all critical equipment. Sequences are multi-step procedures used to control complex operations, such as starting a conveyor system downstream first. In FBD, sequences are implemented using chains of timers and logic gates. In structured text, case-of-state machines are often used. Proper sequencing ensures that equipment starts and stops in the correct order, preventing process upsets and equipment damage. Structured workflow checklist is essential for a successful project study. The checklist includes obtaining the latest CBM file and wiring diagrams, verifying CBM and library versions, mapping all controllers and I/O modules, listing all control module instances, checking task scan times, verifying a CADA mapping, and physically walking the plant floor to verify device locations. Following this checklist ensures that no critical step is overlooked. Start by obtaining the latest CBM project file and all relevant wiring diagrams from the design office. These documents form the foundation of your project study. Ensure that you have the most up-to-date versions to avoid working with outdated information, which could lead to errors during commissioning. Next, verify that your CBM software and all library versions match the design specifications. This step is crucial for ensuring compatibility and preventing issues during commissioning. Mismatched versions can lead to unexpected behavior or even prevent the project from loading correctly. Map out all controllers and I/O modules in your project. This involves verifying that each controller and module is correctly represented in the project and matches the physical hardware installed in the plant. Accurate mapping is essential for reliable operation and troubleshooting. List all instances of control modules such as motors, valves, and PIDs. This inventory helps you ensure that every piece of equipment is accounted for and properly configured in the project. It also aids in troubleshooting and future maintenance. Check the scan times assigned to each task in your project. Ensure that safety-critical logic is assigned to fast tasks while less critical functions are assigned to normal or slow tasks. Proper task assignment balances system performance and reliability. Verify that all signals are correctly mapped between the CBM project and the SCADA system. This step ensures that operators have accurate and timely information for monitoring and control. Any mismatches can lead to confusion or missed alarms during operation. Finally, walk the plant floor to physically verify the location and installation of all devices. This hands-on step ensures that the project configuration matches the real-world setup and helps identify any discrepancies before commissioning begins. Thorough preparation before commissioning cannot be overstated. By following the structured approach outlined in Chapter 1, you minimize the risk of errors, reduce troubleshooting time, and ensure a smooth transition from project study to live operation. Preparation is the key to successful commissioning. Avoid common pitfalls such as using outdated project files, mismatched library versions, or incorrect signal mapping. These mistakes can lead to delays, increased costs, and even safety risks. Always double-check your work and consult the checklist to ensure nothing is overlooked. Effective collaboration with the design office is essential for a successful project study. Regular communication ensures that you have the latest project files, wiring diagrams, and design specifications. It also helps resolve any discrepancies quickly, keeping the project on track. Maintain clear and organized documentation throughout your project study. This includes version control for project files, detailed notes on configuration changes, and records of any issues encountered. Good documentation practices make troubleshooting easier and support future upgrades or modifications. Commissioning engineers should commit to continuous learning. Stay updated on new CBM features, library updates, and best practices in automation. Regular training and self-study ensure you remain effective and adaptable in a rapidly evolving field. Let's recap the key steps for a successful project study. Open the latest project files, verify software and library versions, map controllers and I/O modules, list all control module instances, check task scan times, verify SCADA mapping, and physically inspect devices. Following these steps ensures a thorough and effective preparation for commissioning. A structured approach to project study brings many benefits: reduced errors, faster troubleshooting, improved safety, and smoother commissioning. By following the guidelines in Chapter 1, you set yourself up for success and contribute to the overall reliability of the plant's automation system. Conclusion: Chapter 1 of the CBM Commissioning Guide provides a detailed roadmap for preparing your project before energizing any hardware. By mastering project navigation, understanding controller architecture, verifying libraries, and following a structured checklist, you ensure a safe and efficient commissioning process. Continue to build on this foundation as you move into the next phases of your project.